Now, to describe this property and to do a probabilistic interpretation of impact monitoring, we need to use the notion of target plane. A target plane is a plane which passes through the center of mass of the planet and is orthogonal to the direction of relative velocity of the approaching small body. There are actually two versions of target plane. One is called modified target plane, uses the time T star at which the small body is closest to the planet, and then you take the planetocentric position and velocity at the time of closest approach, and of course, since the distance is minimal, the two are orthogonal, then the MTP is the plane which contains the center of mass and is normal to the velocity at the closest approach. It's a plane which contains the point, the center of the Earth, and perpendicular to the velocity at closest approach. Of course, in this approach, an impact is, let's suppose the Earth is a sphere, the impact cross-section is a disk centered at 0 and with a radius of the planet as a radius. If the vector, the norm of the vector d is less than this radius, we have an impact. If it not, it's not an impact, it is a pure approach. Now, there is a second version of the same, which is typically called target plane or B-plane. Particularly used is called B-plane, also by the people who do you have to take into account that close approach are not always considered as a negative risk. There are some cases in which they are active research, like gravity assist maneuvers. Okay? In the planning of gravity assist maneuvers, navigation engineers have long used a technique which involves the use of a target plane. The target plane is done in this way. If you have a small body or a spacecraft approaching the planet, you take the initial condition, position of velocity, geocentric at the time of the closest approach. If you were to propagate this as a two-body orbit, this two-body orbit, of course, would be hyperbolic with respect to the planet. Then you can take as target plane the plane that contains 0, and this is orthogonal not to the velocity at closest approach, but to velocity at infinity. But this is orthogonal to the asymptote of the hyperbola on which the object would fly if it was just a two-body proposal. Now, so the vector, so what you consider is the limit of the velocity for t going to minus infinity along the two-body orbit. What happens is that the point B, which represents the trace of the close approach on the target plane, is the intersection of a subsymptom with a TP. It's called its length is called the impact parameter, and the impact parameter is more than the minimum distance. The formula connecting the two is like this, where v is the velocity at closest approach. There is another formula also given as function of the velocity at infinity. So what practically happens is that on the target plane, the impact cross-section is a disk of a radius, which is the impact parameter of the impact. The impact cross-section is larger than the cross-section of the Earth by a factor which is typically somewhere between 1 and 2. In some cases, even a little more. Now, why to use this? It looks like a more complicated problem. The reason is you should look only at the last. I don't want to make too much. As a matter of principle, it doesn't matter how you do this, because you just use a representative vector to represent the impact on a particular plane. But because in principle, this function is a smooth function. This is a smooth function of the orbit initial condition. However, not all the coordinate systems are equal. In particular, if you want to use a linear approximation, this is highly relevant whether you have a strong nonlinearity or not. Now, it is, as a matter of fact, the gravitational focusing of the planet introduces strong nonlinearity. So for a very long time, navigation engineers have been using the target plane, even though its formula is more complicated, because they wanted to do linear navigation in the gravity system. And that's why I will discuss in this context rather than the other, even the other is slightly simpler. Okay, so let's define linear impact monitoring. What is linear impact monitoring? You have a given asteroid, you have determined nominal initial conditions, then you propagate it for 100 years. Every time you approach the Earth, within this time span, there is at least one point which is the trace of this orbit on the target plane. So there is a time corresponding to the close approach, and there is a two-dimensional vector on the target plane. Then it is important in this context to note that in reality, even when we speak of target plane, practically speaking, we can only consider a target disk which has some finite radius. For practical reasons, this disk can only be in a given interval, let's say between 0.05 and 0.2 astronomical units. So in reality, you have to think of the target disk of this dimension. Now, let's suppose that the orbit determination solves only for initial condition at some epoch t0. And the differential correction gives us a nominal solution with normal and covariance matrix C and gamma. Then, as the nominal solution is surrounded in the optimization interpretation by 6-dimensional confidence region or acceptable solution, or in the probabilistic interpretation by cloud of probability, in which the nominal solution just mode is point with maximum probability. In the same way, the trace point y star, which is the target plane point determined by nominal solution, is surrounded by a two-dimensional confidence region or two-dimensional cloud of probability in the other interpretation. Now, how do we compute either the confidence ellipse or the probability distribution? As I already explained to you, it doesn't matter which of two we want to consider. Well, we just use the differential of the map which provides the TP trace. Okay, so since I am a mathematician, I feel an absolute urge to prove to you that this map is differentiable, but okay. Essentially, it's enough to prove that the time of the closer approach is differentiable, and then you substitute. And this is given by the implicit function theorem. So there is an elementary argument which says that you actually have a differentiable map from the 6-dimensional space initial condition to the 2-dimensional space, which is target plane. Because the map is differentiable, then you can use the differential, which is the matrix of partial derivative, which is a 2×6 matrix, because you are going to from 6-dimensional space to the 2-dimensional space, which is the target plane. Okay? Then, one of the rules I taught you, and I'm sure you have already forgotten, but you have to go back and check, is that the covariance is propagated in this way. It's not necessary for this matrix to be squared. This is 2×6, this is 6×6, and this is 6×2. And this gives you covariance matrix, which is 2×2. And this is all the computation you need to do to have either a confidence ellipsoid or a Gaussian probability density, which will use the inverse of this matrix gamma y. Remember, this is marginal. That is, it doesn't matter if you have a space, 6-dimensional space to a 2-dimensional space. For each point here, you have a fiber of 4 dimension in the counter image. It does not matter where we are in this fiber. You want to know what is the probability density of being in a particular point on the target plane. Okay? So this is why you compute the covariance matrix, and then the normal matrix you compute the inversion. The confidence ellipse is this. So the linear, if the procedure is linear, there is a simple method to compute directly confidence ellipses, two-dimensional ellipses, or PDF in the target plane. You want to do a computational probability? From this probability density, you get the probability density of on the target plane, which has as mean the image, the trace on the target plane of the nominal, and this matrix gamma y we have computed as covariance. And then this you insert in the integral. We compute the integral on the impact cross section, and this is the probability of impact. Now, this is an integral you cannot compute analytically, but numerically it's trivial because the Gaussian is a very smooth function, so there is no problem in doing this computation. And this gives you the answer. Okay? Now this, if I don't know if there are navigation engineers, but which are specialized in orbit determination, come to spacecraft in this room, but if there were, they would say this we knew 30 years ago. Okay? So this is just standard part of the job for somebody who is in charge of navigation, at least of an interplanetary spacecraft. There's nothing new in this. So, in this case, the applicability of the linearization is well founded. You know why? In a problem of astrodynamics, the hypothesis of linearity is well founded. Let me tell you why. Before making a space mission, you do a mission analysis, which includes a simulation of orbit determination. And then on the basis of this, you decide how many observations you need of the spacecraft to control its trajectory. If you, as a result of forgetting something, you put yourself in a condition for having to do a nonlinear or an orbit determination which is strongly nonlinear, and in particular close approach analysis is strongly nonlinear, the people who did the mission analysis would be fired. Because you must predict the conditions which a spacecraft will be and make sure that the orbit determination remains quasi-linear all the time. Otherwise, you do something else. You do more observation, you increase the investment in tracking from the ground in such a way this does not happen. So please understand, I'm not criticizing navigation engineer because they suppose that orbit determination is linear. It must be in their job. The problem is when navigation engineer start thinking about impact of asteroids. Because then there is a problem. Okay? So, okay, we'll come back on this philosophical question. So now I'm going to tell you a story. The story is a story of 1997 except 11. So this asteroid discovered, as the name says, in 1997. In March of the next year, the Minor Planet Center, which is the official IU repository for astrometric and orbital information asteroid, announced in an email circular and unfortunately also in a press release that the asteroid 1997 XF11 had the possibility of impacting the Earth in 2028. Note that this asteroid is 1 mile in diameter, and just to use the terminology without scientific from a bad American film, this was an extinction level event. That is something which could terminate civilization in orbit. And the Minor Planet Center said that civilization as we know it could be terminated in 2028. You can imagine that the press release made the first page to all the newspapers, in particular in the United States. Few hours later, the JPL Dynamics group announced that the impact probability in 2028 was effectively 0, more than 10 standard deviations. The phrase used by Don Yarkovsky to say this was "it's 0, folks," which is a joke based on it's M, folks, on the last statement of the Method of the Mail cartoons. Okay, so it was even a little bit satirical. So he said it meant actually, this is ridiculous. The number we get is essentially 0. this figure shows the situation. So take the red line. This you may not think it is, but is an ellipse. It's a very long and narrow ellipse in the target plane. It's the linear confidence region computed with the linear method just described. This is the Earth, and this is a this red thing is a 3 sigma limit. So it's visible in this figure that impact with Earth is at more than 10 sigma, and therefore the probability is insignificant. Moreover, a few hours later, a recovery, that is an observation 1997 in Cepheid, which was already on a plate that can be found, was identified in a plate of 1990. And therefore, in 2028, there was not going to be any collision. Actually, the minimum distance was of the order of 1 million kilometers. It's not particularly far. On the next day, Giovanni Valsecchi and myself started working on this problem. And by June, we had ready what I would call a post-mortem, that is an analysis. Okay, I haven't said, but I think you understand by yourself, that this was a particulation catastrophe. That is, the scientific community give the impression they don't know what they are talking about. Okay? We started working on the problem, and our articles submitted this data concluded that both sides of the dispute were wrong. It's not a very nice conclusion. The MPC, because the impact in 2028 was never possible, not even using even without using the observation 1990, the impact was actually not possible. That is, on this, the JPL was right. On the other hand, then the JPL was wrong because they used a linear impact theory. Okay, so if you look at this, now this figure shows a more global view. Not here we are getting to, this is 3 times the distance of the moon. Okay, so this is the Earth. The linear solution is, in this case, is the black curve, and the red curve is a non-linear computation, which is done with particular technique, which don't use anymore, and don't need to explain. Note that this green curve here is a solution which contains observation 1990. That is the ground truth. And this ground truth, the interesting thing is that this ground truth is completely, the confidence region, this ground truth is completely outside the linear confidence region. In other words, near the Earth, because the Earth is near the linear, the difference between linear and nonlinear curves is small when you are close, because these are created by higher order terms, of course. So the difference becomes larger and larger as you go away. So here, in fact, the linear prediction is okay. But what if the Earth was here? Okay, so if actually the Earth had been there, then this is just the tip, an enlargement of the previous figure. So this is the linear prediction, and this curve here is the truth, as determined by using more observation. And you see that the truth is completely outside of the linear curve. And this distance is larger than the diameter of the Earth, which means it is possible, indeed, that the linear theory would completely fail to identify an impact solution, would decide. In other words, the JPL people were right because they were lucky. Okay, not because they were right. Indeed, Brian Martin, MPC, pointed out as a retortion that in a successive close approach in 2014, that was possible. And in this, he was right. And later, when we solved the problem, we proven that by using only the first observation, there was an impact with the possibility of impact of 1 in 22,000 for 2014. Okay, so given the observation 97, if there had been no recovery, the end of civilization was not 28, but 2040, which is not very big difference. Okay, so the question we have here is, can we use, then it is possible to use the linear theory I've just presented to you to compute the impact probability or not? It's simple. The linear theory is always applicable near the nominal solution. If the entire boundary ellipse is just a few 10,000 kilometers, let's say a few Earth-radius, the linear theory is a good approximation. In the contrary, if the confidence boundary is 1 million kilometers long, like in the figure was showing, the eigenterms are relevant, and the linear prediction can be wrong both ways. That is, giving a possible impact where it is impossible, as well as missing an impact possibility. This has a very important consequence. The choice of the method you have to use for impact monitoring depends upon the value of the impact probability we are interested in. That is, because if the probability is close to 1, let's say larger than 0.5, that means 1/2 of the confidence ellipse was inside the cross-section of the Earth. That means the total length cannot be more than a few Earth radius. And therefore, in that regime, the linear theory is applicable. That is, if the probability is high, you can use the linear theory to compute it. On the contrary, if the probability is 1 in 10,000, that means the longest axis of the confidence ellipse has to be thousands of Earth radii. And therefore, the linear theory does not apply. Let's put it another way. If you are a navigation engineer, you are asked to plan a gravity system level in such a way that typically the bosses ask you to guarantee the probability of success of the level of 99%. Because this is your task, you are right to use the linear method. On the other hand, if you have an extinction level event, maybe a probability 1 in a million, or even 1 in 10 million that this happens is relevant. And then you are wrong in using the linear impact monitoring method. That is, the method you use depends upon what is your goal. Let me go back to my philosophical question. I know we are a public of engineers and mathematicians, and we are very different. I'm a mathematician, many of you are engineers, but we have one thing in common. We dislike philosophical questions. Because of philosophical questions, we don't have a simple way to find the criterion of truth. Okay? So we both prefer to handle things we know how to prove with different methods. What happens if somebody asks us a question like this? Down to which probability you wish to be in favor of a possible impact? Unfortunately, even this is a question not easy to answer for us. It is essential, because from the answer to this question depends the mathematical method we have to use. Okay? So if somebody tells you, you want to know the probability of impact only is more than 20%. Giovanni Valsecchi and myself should not have done the work. It was not necessary. Okay? We should have stopped there. The method used by navigational spacecraft is okay. If the possibility of the extermination of mankind is such a catastrophe, even knowing this at the level of 1 in 100 million is necessary, then we have to do a dedicated, concentrated effort to develop the mathematics on non-linear impact monitoring. And at that point, Giovanni and myself personally, and our colleague Steve Chesley, which joined our team soon, had to give an answer to this question. And we unilaterally decided that, yes, mankind was interested in knowing a really catastrophic event, even the probability is 1 in a million. And therefore, we need a new method. Now, how can we handle now to understand what we did, how to find a solution? I need to show you how nonlinearity manifests itself. However, just to do a quick production of this figure, I've used as prediction, not a prediction on target plane, but a prediction on the sky. That is, this figure is showing you are not on target planes, but are on the celestial sphere, or if you want, to the tangent space to the celestial sphere. Because the mathematics is the same. You are projecting from a 6-dimensional space, the initial condition, to the space of 2 dimensions. This shows for one particular asteroid, which was discovered in February 2011, how the prediction on the sky of the position of this asteroid look on the basis of the observation which were available. This object had not been observed apart from a few days around the time of discovery. Now, if you ask this question in April 2011, you see a very, first of all, this is clearly an ellipse. And second, its size is less than 1 degree. If you do the same thing in September, the same year, this already is not an ellipse. It is a little bit asymmetric, but still its size is a few degrees. Do the same in December, it's 10 degrees. Do the same in the next year, 1.5 years from discovery. Not only the region is very elongated, but it also has taken a very clear banana shape. So you easily understand that if you were to use a linear figure, the linear ellipse would be almost completely outside of the banana, and vice versa. It means the linear predictions would completely fail. Then this is another 4 months later. The curve becomes more and more elongated and thin. Why is this? Well, to understand this, the argument is complicated. You have to take into account that we are still behind this. There is a system which actually is Hamiltonian, that was explained by Milani today. And because it is Hamiltonian, the integral flow is volume percent. So if you want to increase the increase of the uncertainty, always manifests itself as something that becomes longer, and to compensate this and maintain the volume, some other dimension has to become thinner and thinner. Now, be careful, because the map to this plane is not canonical. So we are not, this figure do not preserve the area, but nevertheless it is clear that they become longer and longer and thinner, and then more and more curved until something dramatic occurs here. All these have been produced by this system. At some point, the sampling we use to describe the nonlinearity is not enough, and the figure becomes completely wild. That is, even the method we are using here to represent nonlinearity, which is a finite sampling method, fails, because the figure has become completely unmanageable. The object is lost. It could be the right ascension could have any value ascension. Okay, so what you see from this example, what you see is that the region of uncertainty has a fundamental one direction in which expands dramatically, and the other direction in which does not expand or expand in a very limited way. Therefore, what we need to find is a one-dimensional spine of the uncertainty region. That is, we want to find a way to describe most of the uncertainty by a single line. How we do that? Well, let me try to explain this with a simple argument which I invented just for this lecture. To tell me whether it is nice. I have written the differential correction algorithm at some step j. Okay. Now, normally, what you do P transpose P, and then you do the inverse, and you compute the covariance matrix. What happens if this covariance matrix cannot be computed? Let's suppose that the rank of the matrix C, instead of being 6, is 5. What you do? The inverse does not exist. Now, there is a mathematician has invented something which is called the pseudo-inverse. The pseudo-inverse is a matrix which is if a matrix C has a kernel that is a null space, we make the matrix associated to a map which is 0 on the kernel, and the inverse of C restricted to the subspace orthogonal to the kernel. Okay? So I have a matrix which sends an entire eigenspace of eigenvalue 0 into the 0, and in the inverse I still send it to 0. And then for the rest it is an inverse. Okay? This pseudo-inverse has the property that it still provides a solution of this equation. The solution of this equation, this is one solution. The solution is not unique, but it's one solution. And this is the solution of minimum norm. How it works practically. There is a direction in which you have no control, because you actually have no information. The normal matrix with the kind of information you have contains no information. Then you don't change anything in that direction, because in that direction you cannot do anything which has any meaning, so you don't do anything. And then you perform the correction only in the orthogonal space. So, as a matter of principle, you can do it. However, is this useful? Well, not much, because this correction may go in the wrong direction. Nevertheless, let's suppose that this rank deficiency of order 1, that is the matrix C, has always rank n minus 1, has always a one-dimensional null space, applies everywhere. You may think this never happens. It's not true. It can happen if you've done something wrong. But if you have two parameters you have put in the list of things to be determined which are functionally dependent. Let's suppose this happens. Then, can you use an iteration with C star? Can this iteration converge? Can we use systematically, always, at each iteration of pseudo-inverse and get somewhere? The answer is that you can. In principle, you can find the minimum in five dimensions, essentially, in the quotient space. So if we do this, you take the weak direction, which is the eigenvector of eigenvalue 0. This correction has a null component in this direction. If D, that is the right-hand side, in some point in space is parallel to this weak direction, then there is no change. That implies that if this pseudo-differential correction is convergent, the point at which it converges is such that the right-hand side of the normal equation is parallel to the weak direction. So let's use this definition. The points x such that this quantity, b minus b transpose c, is parallel to the null eigenvector, these points are called the line of variation. The equations imposing the parallel of two vectors in n space are n minus 1. So the expression line is not wrong, because this is generically one-dimensional manifold, possibly with some singularities. So this line exists, even in this case. However, this is an argument, it's a very abstract mathematical argument, does not take account of the numerical problem. Let's suppose that you have a matrix C which has positive eigenvalue, 1, 0 eigenvalue, and then all the other positive, but you actually try to compute the eigenvalue or to compute the inverse. If the computation done in exact arithmetic, you will find these eigenvalues. But if there is a comma missing here. this the eigenvalues if the computation is exactly made. And then, if you do the computation on a computer, instead of lambda 1, you can find a very small eigenvalue. What's even worse, the eigenvalue can be both positive and negative. That is, the matrix C should, by theory, by construction, be definitely positive, or at worst case, have a 0 eigenvalue, but we actually can even find a negative eigenvalue. This happens when the conditioning number, which is roughly speaking the ratio between the smallest and the largest eigenvalue, is of the order of the machine relative error of rounding off. So if the ratio between the eigenvalues is 10 to the 16, practically you cannot invert the matrix. If this happens, even if you compute the inverse of the matrix, when you use it, you do such a large mistake in computing the correction along that direction that you would be better off not doing it. Okay? This suggests that we generalize the definition of line of variation. That is, if the matrix is badly conditioned with very small eigenvalue lambda 1, we can generalize the definition of the inverse as a matrix of a linear map which is 0 on the eigenspace of the eigenvalue lambda 1. And is the inverse of C restricted to the linear subspace H, which is orthogonal to V1. So we use the moral equivalent of pseudo inverse not only when I have a 0 eigenvalue, but when you have an eigenvalue which is too small to be confident on the possibility of doing an accurate inversion. Then we can define a constrained differential correction iteration, which is done by using this matrix instead of C minus 1, which you could compute, but you better not. Let's suppose that the process converges. If at this limit point, the right-hand side of the normal equation is orthogonal to this space and parallel to V1 at this point, then the line of points satisfying this parallelism is still called Off-LOV. Line of variation. Okay? The interesting thing is that the line of variation points can be described as local minima of the target function restricted to the interplane H. More exactly, they are minima of some quadratic approximation. To understand this, you have to think to a deep valley. Okay? Let's suppose the space as dimension 3, the space of parameters as dimension 2, and we are showing the graph as the surface of the Earth. We have a deep valley. The sides of the valley are very steep, but in the end there is a river, and the river flows, but flows with a slope which is orders of magnitude less than the slope of the sides of the valley. So the algorithm consists in the following. You start from the side of the valley, and you tumble down along the steep line to the river, and then you stop. Don't move along the river. It does not matter if the river is actually completely flat or the river is slightly sloping in one side or the other. Once you are at the river, you don't move anymore. And this defines a, you might call it streamline. And this is a concept of line of variation. That means, starting from any initial condition, we can start the process of differential correction and find a point of the LOV as the limit. It's a procedure convergence.
Yeah, excuse me. I missed something because if you neglect the direction lambda 1 and you just take the subspace orthogonal to lambda 1, then you miss information on the dynamics in the direction of lambda 1, right? So and then it's a kind of central manifold reduction you do. What you do that is
Yes.
you just take
Yes.
along the non-degenerate directions. But is it meaningful on the global dynamics?
Look,
This is the
you have to understand that again, the nominal solution is not the only solution. What is the minimum? It's not important. What matters are all the points which are not much above the minimum. What matters is the confidence region, which is not one point. Are all those which are not more than 10 meters above the minimum. However, if the river to go down 10 meters takes 10 kilometers, then you have to keep a region which is very elongated in the direction of the river. And this region has as a spine the line along which the line corresponding to the minimum eigenvalue, to the line which is in every point more or less tangent to the line of the minimum eigenvalue. So it is true. What I think is more exact is that what we can get in this way is one solution, which is not necessarily the best solution. However, we are in a situation in which the orbit is weakly determined. And therefore, we cannot represent the orbit by a single point. We want to represent the orbit with 1,000 points. Where should we choose this 1,000 points? We could use a Monte Carlo method. But the Monte Carlo method, because it disperses a point in 6 dimensions, gives a terribly low density. So if we want to do a Monte Carlo, we have to use 1 million points. On the contrary, if you select the spine of the region of confidence, you can have a representation which is close to any point in this confidence region by using a one-dimensional sampling, and therefore you sample in a way which is many orders of magnitude more efficient than the Monte Carlo method. This is the idea. Now, there is another step which is complicated. And the step is the following. Okay, as I told you, in this way you can find one of the many solutions. How we find that? All of them. That is, I don't want just to tumble down to the river. I want to map the river. I want to sample the river. How do I get other points on the river? Well, it's very simple. I am on the river. I move in the direction of the stream. Moving in the direction of the stream, because the river bends, I end up climbing a little bit on the walls. And therefore, I tumble down. Let me show you. This is the example of the procedure. So this one is the nominal solution. Sorry, this is a projection two variables, which are semi-major axis, simplicity, doesn't matter. So this is the nominal solution. Then I move along a direction, which is the direction which is perpendicular to the hyperplane in which I minimize. That is parallel to the vector v1. I do a step in this direction, and I get to this point here, green. And then I do constrained differential correction to tumble down to the river valley. This gives you the RMS of residual. At the first approximation, I get an RMS which is hundreds of times larger than the value which corresponds to acceptable errors. And then I have to iterate until I get to a value which is reasonable. Anyway, the idea is the following. I define a vector field, which is a vector field defined by the eigenvector, and the length is 1 over the square root of lambda 1. Because
the 1 is different from 0.
Yes, of course. So this I'm doing when lambda 1 is small, not 0. This length is the length of the longest axis of the confidence interval. So I move in that direction at a speed, in the direction which is the weak direction, at a speed which is proportional to the length of the confidence ellipse. What I do well, there is a small problem to be solved because the sign, but okay, doesn't matter. I end up by writing a differential equation, and the independent variable in this differential equation is the parameter, and this parameter I use to parameterize the line of variation. However, when we started doing this work in 1998, 1999, we are hoping that the solution of the differential equation and the line of variation defined as the place where there is this parallel to two vectors would be the same. Actually, they are not. Later, my student at the time, Tomei, proved that, well, you know how it works between the supervisor and the student. I say to the student, you prove this theorem which is useful. And the student proved that this theorem is universally false. What can you do? You say, independent thinking. So that's this was a bad defeat. Okay. So the idea is the following: we have a definition of the law and the differential equation. So you do a step along the solution of the differential equation. This is not on the law, and then we have to fall down on the law. So we first do a step in the weak direction, and then we tumble down around the hyperplane, which is perpendicular to the weak direction. And this gives this two-step iteration, which is a way to sample the law. Okay, so this is currently the definition. Of course, the problem is that the parameterization we use for the law is only an approximation, because the truth is that the law is defined by these n-1 nonlinear differential, nonlinear equations. We cannot explicitly compute. By the implicit function theorem, a line exists, and the parameter exists to parameterize this line, but we cannot compute it. So we use an approximation which consists in parameterizing the solution of the differential equation. When we tumble down to the law, we assign to the point on the law the parameter which actually corresponds to the differential equation. Well, that's a tricky thing, but it's not yet all of the problem. The problem is the following. If you have a zero eigenvalue, this is an intrinsic, if you want, topological property of a linear map, the fact of having a kernel. You have an entire subspace which goes into zero. On the contrary, having a small eigenvalue is a metric property. If it is a metric property, it depends upon the metric. Say it in another way. Let's suppose you have coordinates x, and then I change coordinate to another coordinate which I call y. Let's suppose the coordinate change is linear. Y equals Sx, where x is a square matrix. Then the normal matrix is transformed in this way. And the eigenvalue are not the same. Eigenvalue are the same, only the transformation S is an isometry, that is an orthogonal matrix. The inverse is equal to the transpose. So the eigenvalues are not the same. So if I change coordinates, and unfortunately there are a lot of different coordinates in which I can use. As an example, I could decide to compute the orbit in Cartesian coordinate or in Keplerian elements. The definition of line variation is not invariant with respect to this change. So here I have a list of, this is again from this of Tomei, a list of possible coordinates which are normally used in orbit determination. Some of these are similar to some discussed by Menius this morning, are such way that they are non-singular. And then this is an example of what happens to the line of variation. Here I'm showing both the line of variation and what we call the second line of variation, that is the line of variation which corresponds to the second smallest eigenvalue. And you find, so this is a case in which there were 9 observed nights and more than 100 observations, and you see that it is true that the line of variation is not invariant, but still, yes, on occasion. But still they are very close. And the first direction corresponding to the first eigenvalue is very different from the direction of the second eigenvalue for all coordinate system. However, if you have an asteroid which has been observed on 3 nights, what happens is that, well, essentially, the uncertain region is not one-dimensional at all, it's two-dimensional, you cannot find a spine because for the reason that you cannot find a spine to a disk, because the uncertain region is not elongated. And therefore, the definition of the line of variation is completely arbitrary, depending upon the coordinates. So there is no magic formula about which definition, which coordinates, and therefore which definition of log we should use. And that means that the computation of the log done in one particular coordinate might fail in one particular choice for one particular case when the observation, when the orbit is very poorly determined. Okay, I think this is enough. And for today, tomorrow I will describe the line of variation impact monitoring. That is how, by using this method, it is possible to do a non-linear impact monitoring.
Any questions?
I just have a question that's an extension of this, and relevant to an event that just happened a few days ago. The asteroid 2014 RC, which is written by...
Sorry, what's the name of the asteroid again?
2014 RC, which was this house-sized object that passed the geostationary distance, approximately that distance. There was then this meteorite that made ground in Nicaragua. There's some suggestion that it was a broken part of 2014 RC. And I was wondering, in your impact prediction, if, for instance, we were wanting to model the bit of the actual passage of the asteroid, and include things like tidal breakup, things like that, how would you go about extending this to include something like that so that you can...
I think this problem could be treated this formally, but I think in that case, the probability of impact was zero. So that is,
right.
Let's be clear. We use this algorithm every day, and sometimes more than once per day. Every time an asteroid has new observation, we redo the computation. Redo computation means we recompute the line of variation. We propagate along the line of variation and check whether any one of them can impact. In this case, the sentence was that this object was removed from the list of possible impacts. And therefore, because it was removed from the list of possible impacts, the meteorite cannot be a piece of it. Now, this is not a 100% answer. Of course, if the meteorite has been expelled with some velocity, and if the asteroid was actually a comet, which has the capability of ejecting fragments at some relative velocity, then I don't know what the answer could be. But to my knowledge, this asteroid was not a comet at all. So I think this is very unlikely.
Not to be thanked again.